Todd Thomas is the Laboratory Director for Cola Solutions in Cincinnati, Ohio. He started there in 2011 and has worked 25 years in the asphalt industry. He has worked extensively with in-place recycling and reclamation methods and is also involved with preservation products and high RAP hot mix with rejuvenators. Todd graduated from Purdue University in 1989 with a Bachelor of Science in Civil Engineering and in 1993 with a Master's of Science. He is active in ERA and participates in the Emulsion Task Force In-Place Recycling Subcommittee. Todd is a registered professional engineer. Big round of applause for Todd.
Thank you. Morning. It's a pleasure to be here in Nashville at the conference and a pleasure to speak to you this morning. There we go. So yeah, today I'm going to speak on the impacts of pavement preservation and recycled materials on sustainability. I'm going to focus primarily on the flexible pavement life cycle. I won't get into rigid pavement preservation. I'll talk about high RAP HMA. It's not exactly, doesn't exactly fit into pavement preservation, but I think it's relevant for the overall topic. In-place recycling, give some examples on that. Traditional pavement preservation products, and then all of this with sustainability in mind. And I think we all here know that there's an inherent link between sustainable pavement and pavement preservation. It was asked earlier, what's a definition of sustainability? And I have the sustainable pavement there is it's a safe, efficient, and environmentally friendly pavement, and it meets the needs of today while not compromising the needs of those of future generations. And then also, definition of pavement preservation is really to maintain our pavement network in an acceptable way, very cost-effective way that meets, that extends the life of the pavement, that meets the needs of the road users, and all of this with safety in mind. And I look at the two of those as having as its foundation the environmental, economical, and social aspects. So if you look at that, again, pavement preservation and recycling are inherently about sustainability. So from an environmental standpoint, it's the use of resources and a reduction in emissions and energy like we just heard, and it can also be about using more environmentally friendly products. Economically, there's a savings over the life cycle of the pavement as we're implementing pavement preservation, and that gives a savings for the taxpayer. And then socially, when we stretch out that time that we need to do some type of major rehabilitation to the pavement, that's enhancing the value to the motorist. If there's less delay on that, less delay to the motorist due to construction, the more the motorist benefits. So I'm going to talk about the various aspects of the life cycle of a pavement. And I get this from an FHWA Sustainable Pavements Task Force where they looked at, what are some of the key things in the life cycle. So I'll talk about these individually, some more than others. And I'll start with design. And when I say design here, I'm talking about pavement design because, we're starting with some type of a basic pavement structure. And I won't hit on all the key aspects of pavement design, but we'll touch on perpetual pavement design and then the mechanistic empirical design as well. And if you look at the perpetual pavement concept, what we're trying to do here, and this was developed by NAPA several years ago, what we're trying to do is build a very strong pavement foundation, a durable fatigue-resistant layer on top of that, rut-resistant layer, and then finally the surface layer that could be a sacrificial layer in the pavement. I also think, and I don't have it in here because it wasn't in the original definition, but also this is a place at the top for the traditional pavement preservation products like microsurfacing or chip seal. But the concept here is that as a heavy load is placed on that pavement, as you see here, there's high stresses induced in the upper layers the zone of high compression it's called. And then also you get a place at the bottom of the layer there that'll give a tensile strain. So the key is to limit that tensile strain to take a traditional pavement design that's 20, 30 years and extend that way out. And so again, that long life is going to have some inherent benefits, societal benefits, and conserve resources. I also want to, I point out here that we want to ensure that the top layers are recyclable. Sometimes there's different products that are placed between layers that may not be as recyclable. And I'll talk about in-place recycling in a minute. And then there's also, from, again, sustainability aspects, opportunities for high RAP in the high modulus rut-resistant layer. Mechanistic empirical pavement design, essentially what that's doing is identifying stresses and strains in the pavement structure, load or non-load, and then relating those to performance. Now I'll talk about that a little bit more here in a second. Going on to materials processing, I'm focusing mostly on mixed designs and materials selected in the mixed design. There's a lot of other things related to materials, but I'll just stay on the designs here. And a lot of people in our industry have probably heard a lot about this balanced mixed design concept, where we have a great system in the super pave system where we're designing pavements volumetrically, but now as we're getting very high RAP contents, which we'd like to do, with those high RAP contents, now we're challenging the system a little bit in terms of the durability. So a lot of agencies, a lot of companies are looking at going beyond the volumetric mixed design process and looking at the performance-based mixed designs. Again, very important when it comes to RAP and RAS, but now we can throw other things in there like rejuvenators, ground tire rubbers, and different things. So there's a lot of progress being made in the industry. There's a lot of different viewpoints too. And then there's also, beyond the mixed design, there's also a lot on the characterization and in binder testing that's helping us understand what are some key characteristics of the binder properties to give us a more durable pavement. Some of the some of the mixed design tests here, and you'll see is rutting. The rutting test, the Homburg's on the left, the asphalt pavement analyzer on the right. You don't tend to worry about rutting tests when we're putting high amounts of RAP. We're making it stiffer, but as we're putting rejuvenators in that system, we want to make sure that we've not overdosed it in rejuvenator. So we're looking at rutting, and then we have cracking tests, and I showed just two of them there, but there's really several cracking tests that are being used, and that's really, I think, what's helping us to make sure that we have a system where we have enough asphalt content or we have the right rejuvenator in the system, is looking at those cracking tests that tell us a lot about the durability. From a performance-based mixed design, and this is getting more into the mechanistic empirical, we have dynamic modulus, fatigue cracking, and thermal cracking. And again, this is just relating the material characterization to pavement behavior, but again, these are tools that we can use that as we're putting high recycle contents into a mix, if these are working correctly, we should be able to see what's the limit on the amount of recycled material, or tell us a lot about the asphalt content. But there is a large gap between what we're doing on the pavement design and what we're doing in the mixed design and the materials. There's just, you look at how DOTs are organized, there's not normally a link there. And then as we're designing these systems, the pavement designers and the mixed designers aren't really communicating. So there's a lot of opportunity there for improvement. Going on to construction and the life cycle, going to talk more about smoothness here, but there's an importance in building a smooth pavement, we know that, but also as we're doing these preservation treatments, we're helping to maintain that smooth road for the drivability aspects for the motorist. So, the smoother the road, the more comfort the driver is. And there's been a lot of studies show that the lower the fuel consumption is. So some environmental benefits there as well. In-place recycling has the potential to reduce construction time, and I'll show some examples here in a little bit. And again, as we know, pavement preservation keeps good roads good. On the operations side, I'm looking here at either construction or the maintenance of the road, or just the operation of the road in relation to traffic. And really, traffic during the life of the pavement is what's using most of the energy and greenhouse gas. So 98 to 99% of emissions and energy from the traffic over the life of the road, but really I know our focus here is more on construction and maintenance. So on preservation and rehabilitation, go through some things here, and I won't go through the definition again of pavement preservation, but we're using products like chip seals, microsurfacing, crack sealing, thin in-place recycling to help us in those preservation goals. But I'll focus more on the traditional preservation products here, and looking at a study that Gary Hicks did in 5 states, and he presented this at a 2010 California Chip Seal Association meeting. They looked at the life extensions of preservation treatments on flexible pavements, and for chip seals, they found a range of life extension. So chip seals was 4 to 8 years, slurry seal 3 to 7, micro 3 to 8 years, and crack sealing 0 to 4. And a separate NCHRP study found that thin lay had a life extension of 7 to 11 years. Going to a separate study now and looking at the emissions of 3 products here. If you look at the double chip seal, that's just 2 layers of chip seal, or microsurfacing, they have about the same emissions data and energy use. And then if you look at thin wearing course, has quite a bit more in emissions and energy. But if you think of the previous slide I just showed with the life extensions, and they had different life extensions, if you take the mid range of the life, double chip seal 7, micro of 6, and thin HMA of 9. Now that difference that difference is narrowed from what it was. We still see the double chip seal and micro having very equivalent data. The thin wearing course now from the per year emissions and energy has come down, but it's still more than what we see in micro and chip seal. Reconstruction or recycling. Talk about high RAP HMA again. Hot in place recycling. The 2 cold recycling techniques, and then full depth reclamation, and talk about some more emissions and energy data here. So looking at RAP, typically high RAP is considered in a mix to be 25% higher. There's a lot of agencies pushing that upper limit to 40 or even 50%. And I think we know that that's preserving resources. So we have less aggregate use and less asphalt use as we're using more RAP. It's also growing RAP piles in the U.S., and I know certainly around where I live and work, we're producing more RAP than what we're using. NAPA has a lot of guidelines, though, on using RAP and RAS in mixed designs. They have the Black and Green Sustainability book, and there's really a lot of very useful references in terms of how to get high amounts of RAP in the mix. There's also several efficient rejuvenators in the market. I don't know that these are all new, but we're certainly, and it touches on the green chemistry aspects here too. A lot of these green chemistry rejuvenators really do. They are very efficient. They work very well, and they have a lot of benefits. I wish I had more time to talk about that part. Looking at the emissions and energy use, though, of RAP mixes, you'll see the emissions data here with virgin HMA it's going to have the most compared to, say, a 25% RAP HMA. So again, it's showing that reduced emissions from using that RAP. And then if you look at warm mix, which is using reduced temperatures to produce that mixture, that's going to be even less emissions as well. Hot in place recycling. I don't have a lot of data here, but wanted to point this out, and there is a lot of useful information in ARRA's Basic Asphalt Recycling Manual, but it's the on-site recycling of a pavement. You're heating that, you're scarifying it, maybe milling it, you're adding some type of an additive, and usually some type of rejuvenator, and then it's recompacted and used. And there's 3 primary hot-in-place recycling methods listed there, but don't have a lot of time to go into those in detail. From the cold recycling side, and you've heard a little bit of that this morning, 2 processes. One is the cold-in-place recycling, and the other one's cold central plant. So the in-place recycling method is, you think of a train of equipment. Let me make sure my picture might be here. Yeah. You have a train of equipment that, it starts with a milling machine. It mills through the pavement, typically 2 to 5 inches in depth, and it's staying within that asphalt layer. It's not getting into the underlying aggregate layers. And then it's putting that through the equipment, it's mixing it with an additive or a combination of additives, and usually it's asphalt emulsion or foamed asphalt, and then in the back of it, it's going through a paver, and it's compacted, and then it's going to be a base mixture that will be overlaid. In cold central plant, it's essentially the same materials, or RAP if you want to call it that, and we're taking that RAP, using that same additive or combination of additives, again, to make a base mix that'll be overlaid, but this is done at a stationary facility. So here you see where the RAP's being loaded into a mixing unit, and then it's mixed and transported out to the job. And to show you a little bit of data on that, Dr. Charles Schwartz from the University of Maryland has a presentation, I think it's tomorrow, where he's talking about this in a lot more detail. But he's looking at what he calls FSB, or the foam stabilized base, and that's essentially using cold in place recycling or cold central plant recycling. So what he's done is looked at a flexible pavement structure, and it's got a, I'll show you in the next slide. We have a traditional structure on the left. So you have a granular base with HMA base and an HMA surface. And then the right diagram is showing now taking that HMA base layer out and replacing that with the foam stabilized base layer, and it still gets the overlay of the HMA. From, you can see on the right diagram, it's a thicker structure, but overall the 2 structures are equivalent. So if you look at the structural coefficient of the foam stabilized base, he used a value of 0.32. Traditionally, hot mix is 0.4, maybe a little bit higher than that. So equivalent structures, now we're just replacing the HMA base. But what he did in his study was look at the emissions data from that, and you can see, looking at the emissions from a megaton standpoint, the 134 for the HMA. You look at the next highest, the cold central plant on the bottom graph, and it's 42% less than what the HMA is on an emissions basis. If you look at cold in place recycling, it's even less than the cold central plant, even less than half the CCPR. So we get some huge savings in the emissions, and you can look at the color bars there that show from a raw material production plant installation, and what he calls a performance adjustment, and that's has more to do with the density of the materials. So just to summarize on that particular study, that the greenhouse gas emissions for the cold central plant recycling was a 42% reduction from the baseline, and a 80% reduction for cold in place recycling for compared to its baseline. So you do see a lot of environmentally friendly aspects of using the in-place recycling. And a separate case study from France from 2007, and this was using asphalt emulsion. This was on a county road there, and very similar data. Basic design was essentially we're starting with an existing pavement. We're going to, it was milled to 7 centimeters in depth, and then they put a 4 centimeter asphalt binder course with a 6 centimeter wearing course on top of that. Their alternative design was doing the in-place recycling. They still going to 7 centimeters in depth on the recycle layer, but they were not transporting that away from the site. They were doing the in-place recycling process, and then that was topped with the 4 centimeter asphalt wearing course. And then if you look at the greenhouse gas emissions on that, you'll see again quite a bit of reduction. You can see there the cold in-place recycling bars on the left and the conventional treatment on the right. And in every category, you'll see about a 40 to 50% reduction in the emissions by using the cold in-place recycling. If you look at just the performance aspects, and this data is from Washington State DOT, there they looked over a very long time period. They're going out to 10 or 12 years in their pavement management system. And they have pavement structural condition. I don't think it's exactly PCI, but I don't know what the difference is. But pavement structural condition plotted on the y-axis and the age on the x-axis. And essentially it's showing the performance of either the cold in place treatment, which is on the red line, or the mill and fill treatment, which is in the blue line. And if you were to say take a look at the data at 10 years, you'll see the pavement structural condition of the CIR is 80%, and of the mill and fill it's a 40% pavement structural condition. So we certainly see a lot of benefits of using CIR. So it's not just an environmentally friendly product, it's also giving us enhanced performance. And the question here I have is how can we take data like this, and I know a lot of people are starting to do it, but integrate that into the pavement management systems to come up with the decision-making process to use more of these treatments. Full depth reclamation, a little different from what we're doing in cold in place recycling. Now we're using a reclaimer, and we're going through the asphalt pavement layers and into the underlying layers. We're crushing it, pulverizing it, mixing an additive or a combination of various additives, and then it's recompacted and used as a flexible base, at least if asphalt emulsion or foamed asphalt's used. So throw a case study out, and I don't have emissions or energy data on this, but this was published at TRB. There's paper shown there, in Washington Avenue in Las Vegas, Nevada. And this was a road that was 0.7 miles long. It was 4 to 5 lanes wide, a lot of residential areas around it. There were schools and businesses and so on. And they knew the reconstruction in this setting was going to take a very long time. So they were looking at reconstruction time of 120 days. And they got to looking at the alternative of doing full depth reclamation. And so they saw that when they did the project, it took 40 days, so 1/3 of the time. Essentially what they did, they milled off all the asphalt layers, and traditionally in the reconstruction they would have removed all the aggregate base and replaced it and just built the pavement back up to the curb line. With the full depth process, they still milled away all the asphalt layers. Now they did the in-place recycling to a depth of 6 inches, saw they had a better structure, again reduced the construction time, and had a cost savings of 40%. And I think too, you think about material conservation and so on. Just looking at the trucks that were on and off the road, they calculated that there were 3,000 fewer loads of materials trucked on and off the project by using FDR. So I think that right there speaks a lot to the sustainability benefits of it. More to summarize here, going into the gaps. Let me go back to the high RAP content design. So So again, there's been a lot of progress being made on the binder properties needed to reduce the durability issues when we're using high RAP, with or without rejuvenators. But there's more progress that's needed. There's a lot of studies underway. Hang on. More progress is needed, though, on the mixture conditioning in terms of how do we condition a mixture to simulate that plant aging or that field aging, and then two, how do we know what are the best tools to use and under what conditions when we test our mixes, so we have, you know, a very good relationship to what field performance is. And again, from a mix design and pavement design standpoint, there's little to no integration between those two, and really that's wasted resources. There's a lot of improvements that could be made there. I have a good reference here from 2009 TRB paper by Von Quintus and Hall that I referenced to you is on that topic as well. Pavement preservation is really being used, I'd say, by most agencies. There's still progress needed in some areas, but also there's some progress needed in integrating any kind of preservation process or recycling process into a pavement management system. In-place recycling, there's adoption of specs by agencies with a regular program of projects that's needed, and it's good to hear the San Francisco Bay Area, your story where you had a goal you needed to meet, and you had to put projects out there to be bid. If we had more of that, I think we'd get contractors that would say, I need to invest in equipment, I need to participate in that. But there's really been a lot of more resistance on the in-place recycling in some parts of the country. I know there's people in here that have done quite a bit of it in their areas, but I think that is something that as agencies spec it and have a regular program of doing it, you'll see more contractors getting that equipment. I wanted to use it as an opportunity today too, though, to say that avoid putting specs together by just grabbing a bunch of different specs out there and try to piece it together. I've dealt with a lot of specifications where there were good intentions and trying to fuse what seemed to be the best aspect of the specs, but it ended up having a lot of contradictions and a lot of confusion. So want to encourage and point that out and encourage that doesn't happen. There is some research needed on the best QC practices and acceptance criteria in place recycling. I'd say QC is probably down pretty good, but from a assurance standpoint, or how do I know what I designed, and answering that question in the middle of a construction job is there's some research needed there. And I think in general there's a non-use of in-place recycling just due to a lack of education and in some ways in a turf protection as well. So in conclusion, sustainability and preservation and recycling are complementary. They are accomplishing the same goals. Better integration of and improvements in the steps of that whole pavement life cycle is going to result in sustainability improvements. High RAP content mixes save on the use of new aggregate and asphalt and also have lower emissions. Pavement preservation products extend the life of pavements, and the emulsion-based products have a better or lower carbon footprint. And in-place recycling has cost and time advantages with lower emissions and energy use, but it's underutilized. So with that, I thank you, and I'll answer any questions if you have any. The question then on what do you do? How do you get specs implemented? You're required to put a spec, but you're getting input from different vendors or contractors. And I think to me the bottom line there is go to ARRA, the Asphalt Recycling and Reclaiming Association, and they'll work with you in helping to implement specifications that are I guess I'll say generic, but I would reach out to them, and you could find them on the website at arra.org. But they certainly have a lot of people there that can help you out. They have a technical director who is in the back of the room. Steve, will you raise your hand? Is technical director from ARRA. So there are some of those resources out there. Also, ARRA members have been active in the emulsion task force in implementing specifications through AASHTO. Now that's on emulsion. I'm sure similar could be done for foamed asphalt if that's what you're wanting. And it's for CIR and cold central plan. It's not for full depth yet. But I think there's ways to get that done. Any others? All right. Well, thank you very much.